Hi everybody, I'm Laurie, VP of Developer Relations at LlamaIndex, and welcome to our YouTube channel. Today I'm going to be walking through Workflows, our brand new abstraction for building complex agentic applications. I'm going to be walking you through our notebook, which shows you all of the steps in building a workflow and all of the things that you can do with workflows. First, we have to install our dependencies. We just have three: LlamaIndex Core, which is the important one. We're also installing LlamaIndex OpenAI because we're doing one thing with LLMs, and we're installing LlamaIndex Utils Workflow, which is what contains our visualization tools that I'll be demonstrating later. Once we've installed our deps, we bring them in as imports. Having done that, we bring in our OpenAI key from the notebook's secret store because we need it to be able to instantiate the LLM. Now let's look at the most basic possible workflow. It just starts, it does one thing, and then it stops. There's no reason to have a real workflow that's this simple. This is just demonstrating the most basic possible workflow so you can see how they're defined. So most workflows are going to be defined as a class. The class can have any name. So in this case, it's called OpenAI Generator, and it inherits from the workflow class. Within your workflow, you can have as many steps as you want. Each is defined by a decorator called step. Once you've thrown in your decorator, you can define an arbitrary function name, and you use type declarations to define what types of events it accepts and what types of events it emits. In this case, it's accepting a start event, which is a special kind of event, and a stop event, which is another special kind of event. The start event is how the workflow orchestrator knows where your workflows should start. The start, you can have as many as you want, but all starting events will go to all of the functions that have that accept start events. So in our generate function, we're just setting up our LLM. We're calling GPT-4o, and we're using it to complete our query. Our query, we're pulling out of our event. As you're going to see, you can attach arbitrary data to your events, and in this case, we've decided to pass a query. Once we've got a response from the LLM, we call stop event, and we pass back our response as a string. Now that we've defined our workflow class, we can execute it. So first we instantiate our OpenAI generator, and you have two parameters here. One is your timeout, which is how long it will run before halting. It's important to give yourself enough time to actually execute whatever your workflow is going to do. And verbose, which we're going to have false at the moment, but we'll see what that looks like later. Once it's instantiated, you call run on your workflow. We're awaiting it here inside of a notebook that works. If you were running this in vanilla Python, you would need to wrap this function in an async function in order for it to work. We pass the query what's LlamaIndex, and we print the result. And it gives us this response from GPT describing what LlamaIndex is. One of the neat things about workflows is that you can visualize them. We use PyVis to do this. So we call draw all possible flows, and we call it with the class name and what file name the output should go to. And it will generate an interactive draggable diagram that shows all the possible flows within your workflow. I've taken a screenshot of it here. You can see that there's the start event, which goes to the generate function, which just goes to the stop event, and then it's done. There's not a lot to see here yet because we haven't made a complicated workflow. So let's go to a more interesting example, this one demonstrating our ability to loop. We're introducing a few new things here. One of them is custom classes. You can create custom event classes to pass around your workflow. You can create as many of them as you like. You can give them arbitrary names, and you can attach arbitrary metadata to each one. In this case, we've got a failed event with an error and a query event with a query. In the loop example, we've defined two steps. One is the answer query step. It can accept more than one kind of event. This is the other new thing. It can accept a start event or a query event, and it can emit a failed event or a stop event. Because LLMs are so good these days, and I needed this thing to fail sometimes, I'm using a random number generator to simulate failures. In this case, if my random number is 0, then I say emit a failed event. And if my random number is 1, then I emit a stop event, simulating a success. Our second step is improve query. So if answer query emits a failed event, then improve query will pick up that failed event. It can either emit a query event or a stop event. If the random number is 0, then it will emit a query event simulating an LLM improving your query. For instance, if your query failed because it was too vague, you could use an LLM to improve your query and resubmit it. Or if it couldn't figure out how to improve the query, the stop event gets emitted with that result. Let's draw all the possible workflows there. You can see our start event goes to answer query, which can either go to a stop event if it succeeds the first time, or it can emit a failed event, which goes to improve query. Improve query can also fail. It can go to stop event, or it can emit a query event, which goes back to answer query. This is that loop that I was talking about, and it can branch. And you can see how you could, in a complex workflow, put together a whole bunch of these to manage your data moving around your flow. Let's execute this now. This time, when I instantiate it, I'm going to set verbose equals true, which means it's going to output what steps are getting executed. It runs the step answer query, which produces a failed event. Because it produces a failed event, improve query gets run. In this case, improve query produces a query event, which goes back to answer query. Answer query again produces a failed event, which goes back to improve query, which produces another query event, which goes back to answer query, which this time produces a success and gives you the answer to your query. So now we've done looping and branching. Let's talk about state. As a convenience, we have a global state within your workflow. This is super useful for instance, loading data and then making it available to all of your functions. In this case, I'm simulating loading data by creating a database variable with some values in it. I'm doing something new here, which is I'm calling the step decorator with pass context equals true. This means that the a variable of type context will get passed to the function. You can attach arbitrary data to your context using the context.data object. In this case, I'm setting up this fake database and then returning a query event. The query event will get picked up by our query function because it says that it accepts query events. And in this case, it's pulling right back out of the context data the value of some database, which it can then output. We run this with verbose equals true, and you can see that it works exactly as we described. It runs setup, produces a query event, it runs query, produces a stop event, which gives us our result. Of course, this flow is still essentially a linear flow. A more realistic example would be if your start event could either be a query or a data population event, and you needed to wait for your data to populate before you could start answering queries. So let's set that up and see what it looks like. Here's our wait example flow class. Again, we're passing our context, and in this case, if the incoming start event has a data attribute, then we attach it to our fake database variable. Now our query accepts a start event. If it sees a query attribute attached to the incoming start event, then it goes and looks and sees if there's any data in the context data. And if it does, it returns a stop event with the data. If it doesn't, it simply returns none and does nothing. Let's run this. The first time we run, we're going to run with a query. The result that we get is none. So it says, no, you can't, because we haven't loaded any data yet. The second time we run, we attach some data, saying, yes, you can. And you can see that the query step gets run, but there was no event produced by it because there was no query attached to it. What we attached to it was data. But the setup step did run and set up our pulled our data into the context. So now the third time when we run it and we ask if we can kick it, we get the data, yes, we can, because query gets run and produces a stop event. Let's visualize how this flow works. Our start event can go to either setup or query, and both of them produce stop events under different circumstances. Waiting for incoming data like this is a very common pattern, so our context object has a convenience function called collect events. This will capture events and store them, and it will return none until all of the events that it has been specified to collect have been collected. Those events will then be attached to the output of collect events in the order that they were specified. Let's see what that looks like in practice. In our collect example flow, we have three types of custom events: an input event, a setup event, and a query event. And we have three functions: setup, collect input, and parse query, each of which accepts a start event. The setup event runs only the first time, and it sets up some data in the context, and then it emits a setup event. The collect input function will run if it sees an input attribute on the incoming start event. If it does, it emits an input event. The parse query event simulates a query. If it sees a query attribute, then it outputs a query event, which will then get, then all three of these will get collected by run query. Run query, we've specified, accepts an input event or a setup event or a query event. And the first line calls collect events and specifies that we want a query event, an input event, and a setup event. If all three events haven't happened yet, then what ready will return is none. So this function prints not enough events yet until it has seen all three events happen. If it's seen all three events happen, however, it says, now I have all the events, and shows us the output of what ready is. So let's see this running. First, we call run, and we can see that the setup event runs, but run query says not enough events yet. Then we run with some input, and you can see the input function runs, but still not enough events yet. And then the third time we run with a query, and it says, I've got a query, and now it says, I have all the events, and it shows us what's in the output of ready. The important thing to notice here is that the output of ready has these events in the same order that they were specified. So in collect events, I said, give me a query event, an input event, and then a setup event. And you can see here, a query event, an input event, and then a setup event. We can also visualize this, so we can see a start event going to parse query, collect input, and setup. In all three cases, you can see them emitting their specific type of event, and those events all going to run query, which is what calls the stop event. Another thing you might want to do with collect events is to monitor failures. In this case, we're calling a failure example flow, which tries to do a thing, in this case, generate a random number greater than 5. If it's greater than 5, there was a success, and it calls a stop event saying that there was success. If not, it emits a failure event. The monitor failure function accepts failure events, and then it has a collect events call, which is waiting for 3 separate failure events. If there haven't been 3 failure events, if there have been 3 failure events, then failed will be not none, and it will print that the simulation has failed and emit a failure result to the stop event. So now let's call this 6 times in a row and see what happens. First, there was a failure, so it returns none. Then there was a success, so it returns success. Then there was a success, so it returns a success. Then there was a success, so it returns a success. Then there was a second failure, so it returns none. Then there's a third failure, and now it says that the simulation has failed. And you can see that our failure events are different, and it has collected all three separately. The visualization here is again pretty simple. You can see it's calling try to do thing. It can go to stop event if it succeeds, or it can emit a failure event, which goes to monitor failures, which also goes to stop event. The final thing I'm going to demonstrate is stepping through a workflow step by step. This is really useful for debugging. I've instantiated a new copy of failure example flow here with verbose equals true, and instead of calling run, I'm going to call run step. You can see that it runs the step try to do thing, and that there was a failure, and that it produced a failure event. Then it waits until I call run step again. Then it calls monitor failures because that failure event was waiting for me to run steps. And then monitor failures produces a stop event. We can visualize this using draw most recent execution. In this case, it calls the instance of the class rather than the class name, and we give it a file name again. It outputs this file, which says there was a start event, which went to try to do thing, which generated a failure event, which went to monitor failures. You can see how this would be useful for debugging step-by-step a complicated workflow. That concludes our tour of creating, running, and visualizing workflows. Feel free to check out the show notes with docs, examples, and the link to this notebook. Thanks for listening, and I'll see you next time. Bye.